Hello everyone, this is our 8th tutorial. Okay, so we'll discuss tutorial 8. Today we'll discuss diagonalization and invariant subspaces. So what is diagonalization? Uh, Given a matrix A, if there exists given A n by n matrix, if there exists P, another n by n matrix, non-singular P n by n matrix, which is non-singular, such that P inverse AP is a diagonal matrix then A is called diagonalizable. Okay. So what is the meaning of this? So recall that a matrix n by n matrix represents a linear transformation from Vn to another vector space, means same vector space Vn. Okay, and P inverse AP. So if this T is transformation is given by the matrix A, then P inverse AP is the same transformation with respect to a different basis. Okay, same transformation, same linear transformation with respect to a different basis. Okay, so note those two A and P inverse AP represent same transformation. That's why they are called similar matrices. Similar matrices. A and P inverse AP are called similar to each other. Okay. So we are interested to see if a matrix is diagonalizable or not. Why this is interesting? Because uh, if suppose A is diagonalizable, then there exists basis which will by which the matrix representation will given by some diagonal matrix d1 d2 up to dn. They may not be distinct. So this is the representation of the transformation. Now it is easy to see that if we take the basis alpha 1 up to alpha n, then with respect to this basis, suppose the matrix representation T with respect to this basis is this diagonal matrix, then it is easy to calculate T alpha is, right? T alpha is are simply those di times alpha. It is just scaling of that dj times alpha j for j all j equal to 1 up to n. So if okay, then we can easily compute arbitrary composition. That is, if we want to construct, we want to compute t to the power n alpha j or t to the power some m alpha j, it is just applying t to the power m minus 1, now t alpha j, but t alpha j is same as dj alpha j. So we'll get dj by linearity, this is same as dj times t to the power m minus 1 alpha j. And inductively, this process will be repeated and we'll get d to the power m times alpha j. Okay. So note that this kind of, it is easy to compute what will be the effect of composition of t n times, right? In other words, it is now easy to compute this kind of thing. Suppose A is some diagonal matrix d1 up to dn, then a to the power m is same as, you can multiply m times. So, and if you multiply two diagonal matrix, only the exponent of the diagonal entries will increase. Okay, this is diagonal entries are probably non-zero, and other entries are actually zero. Then a to the power m will look like this. So this is the importance of diagonal matrix. Now, suppose P is A is diagonalizable. If A is diagonalizable, suppose A is not diagonal matrix, but it is diagonalizable. Can we compute A to the power m easily? So the answer is yes. Then what happens? P inverse AP is some diagonal matrix, right? And then what we can do is simply compute, or A, we can write A equal to PDP inverse. Therefore, A to the power n is same as PDP inverse n times, right? Then again PDP inverse, it will continue. But we can cancel those inner terms, PP inverse, those will be cancelled, right? So eventually what we will get is P d to the power n P inverse. Okay. So let us see an example how we can easily compute matrix exponential if we know it is diagonal. Probably my it is not. Okay. So an example. Let us see an example. Let us consider a to the power n. Let uh, given a equal to this matrix 0 1 1 0. Recall it actually represent um, this transformation txy equal to y comma x in R2, right? Okay, is the matrix representation of T with respect to standard basis. Okay. Now, in this case, it is actually easy to compute a to the power n, because a to the power n correspond to this t to the power n, and t to the power n will look like applying t n many times. So either it will look like x comma y or y comma x. This is if n equal to even. Apply, if we apply t two times, then it is actually identity. So we can, this is identity transformation. So t to the power n will be identity if n is even. So we can say t to the power n. There are two possibilities. One is if n is even, then since t square is identity, we'll get identity here. But if n is odd, then this will look like T. Right? So here it is not interesting to compute a to the power n. We are not interested. Okay. Forget this example. Let us compute another where we can use diagonalizability to compute this n times, means a to the power n. Okay. So let a equal to this matrix 1, 2, and sum is 3 and determinant. Okay. This is 1, 2, 1, 1. Determinant is 1 and trace of A is 3. So product of the eigenvalues, instead of making determinant 1, let us change slightly to trace is okay, take 1 minus 2, then trace is minus 1. Or it is okay, let us not worry. Okay, the question is what will be the eigenvalues of A. So here we need to compute A to the power, suppose we need to compute A to the power 1000. Okay. Now it is obvious that direct computation is not that straightforward, because we need to take, means we need to compute a lot. There are, for each operation there are lots of multiplication and lots of addition. So direct computation is not easy in this case. But the claim is we can compute A to the power 1000 using that diagonalization. Okay. So recall that eigenvalues are given by this. Let lambda be an eigenvalue. Then A minus lambda I times phi equal to 0, or determinant, we know if lambda is an eigenvalue, then determinant of this is 0. Now 1 minus lambda, 1, 1, 2 minus lambda, 0. From here we get lambda square minus 2 lambda, then minus lambda, that is minus 3 lambda plus plus 2 plus 1 equal to 0. Instead of 1, let me slightly okay. So what we can do is let us change it a little bit. Okay. So from here we can calculate the eigenvalues. So lambda is 3 plus minus root minus 3 square which is 9 minus 4 AC by 2. So 3 plus minus root 5 by 2. Now the so for let us try to find eigenvectors corresponding to this lambda 1 and lambda 2. Okay, let lambda 1 is 3 plus root 5 by 2 and lambda 2 is 3 minus root 5 by 2. Now we want to find eigenvector corresponding to lambda 1. Okay, eigenvector correspond to lambda 1. So it is given by, so we only need to consider the first row because we don't need to consider, so we want to consider this equation, right? A minus lambda I times, let us assume p1 p2 is an eigenvector or x1 x2 is an eigenvector. Be an eigenvector corresponding to lambda 1. Then A minus lambda I times x1 x2 equal to 0, but A minus lambda I times x1 x2 will give me two equations. One of the equation is linearly dependent, so we only considered the equation corresponding to this first row. That will give me 1 minus lambda x1 plus 1 times x2, which is x2 equal to 0. From here we get x2 equal to 1 minus lambda times x1. But 1 minus lambda, here lambda is lambda 1, so it is, we need to subtract, which will give me minus 2 minus root 5 by 2 times x1. Oh sorry, it is minus of this, so okay, lambda minus 1. Similarly, if we assume okay. Similarly, if we assume x1, x2, so here we can choose. So therefore, from here it is clear that if we choose x1 equal to 1, and then x2 will becomes 2 plus root 5 by 2 is an eigen value, eigenvector correspond to lambda 1. Okay. Now similarly, if we assume x1 x2 be an eigenvector correspond to lambda 2, then again that the same equation a minus lambda I times x1 x2 equal to 0, that will give me 1 minus lambda times x1, so 1 minus lambda times x1 plus x2 equal to 0, this equation. And there is another equation, but that is dependent on this because determinant is 0, so another equation will be completely determined by the first equation. Now 1 minus, what is the value of lambda? It is lambda 2 is 3 minus root 5 by 2. So again we get the same solution, x2 equal to 1 lambda minus 1 times x1, and this is 3 minus root 5, that is 2 minus root 5 by 2 times x1. Therefore, by the same observation, 1 by 2 minus root 5 by 2 is an eigenvector correspond to lambda 2. From here, it is clear that we can put those two things, a times this v1. Here, what is the matrix A? A is 1 1 1 2. A times 1 1 1 2. Sorry, A is this matrix. Okay. I want to say A times v1. So v1 is this vector, right? And v2 is this vector. So we already got that A times v1 is lambda 1 v1, lambda 1 v1, and we also got that A times v2. If we write A times v2, that is same as lambda 2 v2, right? We get a matrix equation like this. So we may write, instead of writing like this, we can construct a matrix using v1 v2, and we can put it in columns. So v1 is now 1 by 1 and 2 plus root 5 by 2, and v2 is 1 2 minus root 5 by 2, right? This is same as lambda 1 lambda 2 we can put. So whenever we get this kind of situation, then we can put this as diagonal entries and v1 v2 as columns. Note that if you multiply those two things, you will again get this kind of uh, matrix. So lambda 1 is 3 plus root 5 by 2, lambda 2 is 3 minus root 5 by 2, and now v1 v2. 1 2 plus root 5 by 2 and 1 2 minus root 5 by 2. So what we have got is, because this is our p, so we get a times p, a p equal to, this is, if we assume this is p, the right hand side is p times diagonal matrix. This is our diagonal matrix. Okay, so we get p inverse ap equal to d, and therefore a is same as p inverse dp. So we need to calculate a to the power 1000. This is same as p1 p inverse d to the power 1000 p, right? So now the calculation is easier, because though it is not very straightforward, because here we have irrational entries, so again we need to calculate, but we don't need lots of multiplication, right? It is same as p inverse. So what will be p inverse? P is this matrix, so we can easily compute p inverse for 2 by 2 matrix. It is 1 by determinant of this matrix, but no, what will be determinant? 1 times this minus this. So it is 2 minus root 5 by 2 minus 2 plus root 5 by 2. So that is same as minus 2 root 5 by 2, right? That is minus root 5. So 1 by minus root 5 into this is 2 minus root 5 by 2, and diagonal will be exchanged, and we need to put negative sign for other entry. Minus of 2 plus root 5 by 2. And now we what we will do is 3 plus root 5 by 2 times 1000, and 3 minus root 5 by 2 times 1000. Those are 0 zeros, times p, and p is 1 1, 2 plus root 5 by 2, 2 minus root 5 by 2. So I want to emphasize this, that though a to the power, for a to the power 1000 we need to compute a lot. We need to multiply all those rows and columns, and we need to also add those things. But here it is relatively simple. We only need to calculate this to the power 1000, this to the power 1000, and this matrix multiplication. There are three matrices, and we only need to calculate this three matrix multiplication. So this is relatively easier. Okay, though I have made a wrong choice, we are getting some irrational kind of eigenvalues that is making our calculation difficult, but but still it is interesting to see that the whole calculation becomes is becoming equivalent to calculating this three matrix multiplication. There are only three matrices. Okay, so this is how diagonalizability will help. Let us see another thing, which is called invariant subspaces. So let T be a linear transformation. T maps phi to phi. It is a linear transformation. Then W, a subspace of phi, a subspace is called T invariant if T of W containing W. Okay. So the range of this W, the range of T with domain W should contain in W. So can you give me some T invariant subspaces? Example of T invariant subspaces. So if we choose W equal to 0, then note this is always T invariant, right? T of 0 is same as 0 belongs to W, right? So this is a T invariant example, T invariant subspace. And again, if we choose W equal to phi, then note that T of phi, by definition, it lies in phi. Okay, so again, it is T invariant subspace. Now, what are some non-trivial example? Another trivial kind of example is choose W equal to kernel T, right? Then T of W, if we apply T on elements of W, that will give me 0, because T maps on, by definition, T applied on X will be 0 if X belongs to kernel of T. Kernel of T. So this is the singleton set 0, which is contained in phi W. Sorry, because 0 belongs to every subspace. So this is also an example. And similarly, if we take range of T, W equal to range of T, that is, it is also denoted as TV, then note that every element of, so if we assume X belongs to W, then X will look like X, or some phi belongs to W, then phi will look like, then phi equal to TW for some W belongs to phi. Sorry, W belongs to W. Now again, if we apply T on phi, that will give me range of T, domain is V, so it is from V. So it is T of TW, right? So we actually do not need anything. It is automatically in, if W belongs to range, then it is again in range of, okay. So it is straightforward actually. Because T square of T of W is same as T square of V, and this is containing TV. So all those are some very obvious kind of example for T invariant subspaces. Another interesting example will be eigenspaces. Okay, so let E lambda be eigen be an eigenspace correspond to lambda, eigenvector eigenvalue lambda. Then note that T of, so if V belongs to E lambda, Tv is same as lambda times V. But lambda times V also belongs to E lambda, right? Because V belongs to E lambda, by definition of subspace, scalar multiplication should also lies in E lambda. Okay, so we are getting that T times E lambda is containing E lambda. Hence, this is also T invariant subspace. Example of T invariant subspace. Okay. Consider this kind of projection. T projects a vector x comma y to this x comma 0. Then it is clear that all the elements in x-axis will be T invariant. That is, it also same as this, because all the elements will maps to this x-axis, and x-axis is the range. So it is also T invariant from this uh, observation. But it is also clear directly that any vector on x comma 0, if we apply T, it will again land here. X comma 0 maps to x comma 0. Right? So those are actually some example. But if we take the subspace, this kind of subspace, this diagonal line, the subspace of x comma y, such that x equal to y, then it is clear that it is not T invariant, because all the elements uh, except non except uh, the zero vector will maps to some different subspace, right? It, this x comma y, x comma x will map to x comma 0. So image of T, if we apply T on this subspace W, this is our W, then it is not lying in W. So this subspace is not T invariant. Okay, so those are some examples. Now let us try to compute, try to calculate, try to solve some problems. Okay. Here the 4 by 4 matrix is given, right? Then which of the following statement is correct? Is our answer. So note that though A is 4 by 4 matrix, it is a block lower triangular matrix, right? You can make, you can divide the matrix as block 2 by 2 matrix, where note that the matrix is looking like this: A 0 some B and C. And you can easily compute determinant for this kind of matrix. If it is a block upper triangular or block lower triangular, then the determinant is same as determinant of A times determinant of C. So B does not have any role in this kind of situation. Okay. Now we need to find characteristic polynomial of A. So characteristic, note that characteristic polynomial. So this is our A. So instead of writing A again, let me write some D or BCD. Okay. So characteristic uh, equation is same as determinant of A minus. Okay, here characteristic polynomial. Characteristic polynomial. So for characteristic polynomial, actually it is started as this determinant of xi minus a instead of a minus xi, because the problem is a minus xi may not give you the monic polynomial. We need to change the sign. Sometimes we need to change the sign depending on the size of matrix. So that's why we just rearrange those terms. Not rearrange, but we need to take xi before a. Okay, so that will give me determinant of this matrix, right? I have assumed a equal to this, a equal to this matrix. So we are calculating now. We are calculating determinant of this. So it will look like xi minus d, and so b will be unchanged because does not b does not have any diagonal entry, right? Diagonal entries will appear in A, and it will appear in it will appear in D, and it will also appear in C. So B will not change by this subtraction, and this is xi minus C. This is again unchanged, right? So this is same as determinant of xi minus D into determinant of xi minus C. So in our case, D is this matrix minus 1 to 2 1. So minus 1 to 1, and we are trying to find determinant of xi minus this d, right? So we need to, okay, so instead of in this case, note that sign will not change actually. Okay, if we subtract x, then this is because it is 2 by 2 matrix. Therefore, determinant of xi minus d is same as determinant of d minus xi, since d is 2 by 2 matrix. Okay, that's why this is true. Otherwise, it is not true. So 1 minus x times, okay, this is same as x minus 1 times x plus 1. So this is x square minus 1 and minus 4. That is x square minus 5. And similarly, determinant of xi minus c is same as c is this matrix 1 2 0 0, which is again some diagonal, means upper triangular. So it is actually x. It will become 1 minus x times minus x. That is x times x minus 1. therefore this determinant will becomes x times x minus 1 times x square minus 5. Okay, so yes, it is clear that characteristic polynomial is different, right? This is x times x minus 1 into x square minus 5. Now, yes, so this is the characteristic polynomial. A is not diagonalizable. Is it true? So you can see there are 4 eigenvalues, 4 distinct eigenvalues. Okay, which are, so this will give me x equal to 0. So 0 is an eigenvalue. This will give me x equal to 1 if we equate with 0. So this will give me x equal to 1. So 1 is an eigenvalue, and this will give me x equal to plus minus root 5. So root 5 and minus root 5. There are 4 different distinct eigenvalues. So in this case, we have already seen if all eigenvalues are distinct, they will give me only a single eigenvectors. So in this case, both algebraic multiplicity of some eigenvalue, it is already 1. It is clear. And in this case, geometric multiplicity are also 1. Because there can be at most 4 eigenvalues. It is 4 by 4 matrix, so there can be at most 4 eigenvalues. But we also see that corresponding to each different eigenvalues will get a distinct linearly independent eigenvector, right? So that forces that eigenvector corresponding to these distinct eigenvalues are actually same as there is only one linearly independent eigenvector, or we can say the size of eigenspaces or dimension of these eigenspaces are actually 1 in this case. This is forced, right? So always recall that if there are distinct eigenvalues, then algebraic multiplicity and geometric multiplicity both are 1 in this case. And when algebraic multiplicity, geometric multiplicity are same for all eigenvalues, then it is diagonalizable. So this is actually false. And we have already seen geometric multiplicity is actually 1. So D is also. Up to this, is there any doubt? Okay. So let us see this problem, new problem. Here T and U are two linear operators which commutes. It is given that T times U is same as U times T. This relation is already given. So we need to check if option 1 is correct or not. So NU denotes null space of U. Okay. Recall the null space is defined by all those vectors in V such that T of V equal to 0. This is the definition of null space. So if we assume V belongs to NV, then what happens? V belongs to NU. We need to prove or disprove that NU is T invariant. So to check if T of NU containing NU. Okay. If we apply T on the subspace, if it containing that subspace. This is the definition of T invariantness. Okay. So V belongs to NU, that will imply uh, T times, sorry, okay, we are trying to see T of V belongs to NU or not. So how we can see? We just apply U on TV. Okay. So by definition, this is same as TUV by star. Okay, star will give me this equality. But V is coming from null space of U. Therefore, U times V will give me 0. T0, which is 0. From here, it is clear that T applied on V belongs to null space of U. That is U NU containing, sorry, T NU. We have applied T on null space. So this is actually true. Therefore, NU is T invariant actually. NU is T invariant, so A is false. Now, is it clear that RU is T invariant or not? This is for A. For B. Okay. So again, we start from some element coming from RU. Let phi belongs to RU. Okay. So range space of U. That means V equal to some U times W for some W in the vector space. Now, what happens if we apply T on this elements from RU? This is same as TUW, but again TU and UT are same. So this is UT of W, right? Again it is by star. So this containing, this belongs to U of range space of U. So again, if we apply T on any element coming from the range space, that will again belongs to range space. Therefore, it is clear that RU is T invariant. So A, B both are false. Now what about NT plus RU? Is it T invariant? Okay. For C, we already have seen that null space of T is T invariant. Okay. And RU is T invariant is proved in RU is T invariant by B. In this case, RU is also T invariant. Therefore, their sum T of NT plus RU, it is true even for anything, for any two vector space, U1 and U2 be two vector space. In this case, if you apply T on the sum, this is same as TU1 plus TU, right? This is simply because T is linear. If you add two element and apply T, that is same as applying T individually and adding after the application. Okay. So RU is also T invariant, therefore T of nt plus ru is same as t nt plus t ru, but t, nt is t invariant, so it contains in t, it contains in nt, and this is t invariant, so we get this belongs to r. Okay, therefore nt plus ru is t invariant. So C is correct. Now what about RT and NT are are invariant under U? Is it true? We have already seen that NU and RU are T invariant. Okay, so just change the role of U and T, right? If we change the role of U and T, because U and T are satisfying some symmetric kind of relation. So changing the role of U and T, that will give me the answer D, because we have already seen that in option A, NU is T invariant. So by the same kind of process, NT will be UN invariant. And here we have seen RU is T invariant. By the same method, we'll get RT is UN. Okay. Now the next question. Here we need to check if the matrices are diagonalizable over real number. So in this case, note that all those matrices are actually upper triangular matrices. Oh no. So this is upper triangular, this is upper, and this is lower triangular matrix. So we already know that eigenvalues of a triangular matrix is same as diagonal entries. So we need to check diagonalizability. And how we can check diagonalizability? We know a matrix A is diagonalizable if so if the whole n by n, or in this case it is Rn or Cn, whatever we take the field, that field f to the power n is same as the sum of the eigenspaces, and this is possible if and only if algebraic multiplicity of eigenvalue is same as geometric multiplicity of the corresponding eigenvalue for all eigenvalues lambda. Okay, in that case it is actually diagonalizable over complex field, but to be diagonalizable over R, we need to, in addition, we need to see that all those eigenvalues should be real number, and the corresponding eigenvectors are also some element in Rn. So in this case, first for option A, here the eigenvalues are, the diagonal entries are 1, 1 and 2 eigenvalues. Here it is 2, 2, 3, 1, 1, 2, 1, 2, 2. So one vector is okay, one vector is distinct. So we only need to check, in this case, if a vector appears once, then for all those kind of vectors, algebraic multiplicity and geometric multiplicity both are same. Okay, algebraic multiplicity 2 is same as geometric multiplicity of 2, both are actually 1. So we don't need to worry about those kind of vectors. So those are okay. Algebraic multiplicity, sorry, this distinct vector, if it is appearing one times, then algebraic multiplicity and geometric multiplicity both are 1. So you only need to worry about the repeated vector. Okay. For option A, note that algebraic multiplicity of 1 is 2. It is appearing 2 times. Now we need to find geometric multiplicity of eigenvalues. So again we recall that geometric multiplicity of lambda is same as null space. So nullity dimension of null space, that is nullity of A minus lambda I. And this is same as rank of A minus lambda I. We need to subtract it from n, right? So in this case it is 3 by 3 matrix, so n equal to 3, and we also see that A minus lambda I, lambda is 1 in this case, A minus I, it is actually 0, 1, 0, subtracting from the diagonal, and above entries are 1, 0, 0, right? So this is what the matrix will look like. So here you can see that rank of A minus I is actually 1. There is only one linearly independent column. Therefore, geometric multiplicity of this lambda equal to 1 is same as 3 minus 1 by this n minus rank of this. So, therefore, algebraic multiplicity and geometric multiplicity are same. For all eigenvalues lambda, therefore A is diagonalizable, right? So here we don't have any problem, and moreover, it is up to now we only know that A is diagonalizable over complex field, because we don't know what are the eigen means. In general, it may not be diagonalizable over real number, but in addition, note all those eigenvalues are real. All those eigenvalues are real, right? Therefore, and also the matrices are real. Therefore, the corresponding eigenvector will be also real eigenvectors. All those entries in some eigenvectors will comes from real number. Okay. So therefore, it is not only diagonalizable over C, it is also diagonalizable over R. Okay. So up to now, it is diagonalizable over C, but here all eigenvalues are real, and the matrix A is made of real entries. Therefore, eigenvectors are also real. So now eigenvectors and eigenvalues both are real. Therefore, A is diagonalizable over real. Okay. So 1 is correct. Now what happens for this option? So we need to find geometric multiplicity corresponding to 2. So if we subtract 2 from the diagonal entries, this becomes 0, this becomes 0, this becomes 1. Now what is the rank of this a minus 2i? What will be rank of this? There are two non-zero linearly independent columns, right? So rank of a minus 2i is actually 2. Hence nullity is 1. Okay. For option B, rank of a minus 2i is 2. Nullity is 3 minus 2, which is 1. So, so this is strictly less than algebraic multiplicity of, right? Therefore, it is not diagonalizable. So B is not diagonalizable. And what about this? Again, if you subtract 1, then this becomes this matrix 1 from the diagonal, and you can see that in this case also rank is 2. Hence nullity is 1, which is strictly less than algebraic multiplicity. So geometric multiplicity in this case is strictly less than algebraic multiplicity. Therefore, this is also not diagonalizable. What about D? For D, again we subtract 2, right? 2 is appearing twice. So if we subtract 2, this becomes minus 1, this becomes 0, 0. So rank is 2 by the same method, same technique. This is not diagonalizable. Is there any doubt up to this problem? Okay. So let us see the next problem. Here is 4 by 4 matrix.
Excuse me.
Yes.
For a real vector space, can you have a complex number as eigenvalue? That linear operator defined on a real vector space, can that linear transformation can have a
Complex eigenvector. So
complex?
it depends on the definition. So if they actually they it should not, because eigenvectors, eigenvalues are defined over the same field.
Same field, because the definition itself is lambda in that field is said
Yes.
to be otherwise lambda v may not be defined. If alpha is a complex number and v belongs to a real vector space, how can you talk of lambda v?
Yes, that is true. You are correct in that case. But
But in the last assignment, they have marked wrong.
okay, so
That
the
is assignment.
problem
Hmm.
is due to convention. So for matrices, if A is n by n matrix, then
Hmm.
people also define, also say that lambda is eigenvalue. Lambda is an eigenvalue if determinant of A minus lambda I is 0, and they they also include complex eigenvalues in this
Okay,
case.
but it is a transformation. T is a linear operator on a finite dimensional vector space.
Yes, then it should not be called eigenvalues.
But given they have cut marks for that one.
Okay,
In the
then
assignment
then
7,
you can raise
assignment
that
is
issue. Actually, you can ask them.
Assignment 7, question number 1.
Okay, then you can ask them to resolve this.
It is not for matrix, it is for a linear operator defined on a real finite dimensional vector space.
Okay, then you can ask them. But it actually depends on convention. Usually, it should not be called eigenvalue if you follow
Because a
it.
lambda v will not be defined.
Yes, exactly.
When lambda is complex and v belongs to a real vector space, how can you talk of lambda v when lambda is a complex number?
Exactly. That should not be called eigen. So you can raise that issue. But is there any doubt for these problems?
Oh, no problem. Please, can you raise that point?
Actually, I cannot say, but you can ask because you are able to chat in that Google forum or something.
Okay.
You can ask the moderators. So in this case, it is again block. If you think it as a block matrix, some B, C, D, then this is a zero matrix. So it is block lower triangular matrix. So we can easily find characteristic polynomials. Characteristic polynomials. It is given by determinant of xi minus a, which is same as determinant of. So we just need to subtract all those things. But we have already seen that if you subtract x from all those entries, this is nothing but determinant of minus 1 minus x to 1 minus x times determinant of another thing, right? This times determinant of 1 minus x minus x 2 minus 1 minus. Oh, I have already solved that one. Probably the same. Okay, it is slightly different. Minus 1 to 2 1 2 2 1 0. Oh, it is different actually. Okay. So determinant of this will be uh, same as that determinant is already calculated because this is same as this. Minus 1 to 2 1. It is x square minus 5 2. This is actually x square minus 5. Now what is determinant of 1 minus x? 2 minus 1 minus x minus x. This is same as x square minus x minus 2 times 1 plus x. That is same as x square plus x plus 2. So from here uh, we get, okay, we cannot factorize further. 2 minus 1. Oh, yes. So it is x square plus x plus 2. Now this is the characteristic polynomial in this case. Oh, sorry. This, there will be no minus x because we are only subtracting from the diagonal. That is what, like, x square minus x plus 2. Okay, but we are getting the same thing. So the characteristic minimal polynomials are same. Minimal. So let me say about minimal polynomial. Define minimal polynomial. Minimal polynomial is the least degree monic polynomial. Least degree monic polynomial Px such that Pt equal to 0. Okay, so minimal polynomial for a transformation T is the least degree polynomial Px for which Pt equal to 0. So in general, but we also know why Hamilton theorem that every matrix or linear transformation, both are same, satisfies its characteristic equation. Characteristic equation. So we also have that characteristic. If we take the characteristic polynomial chi t, chi x, then it should be clear that chi t is also 0, right? So, so the fact is that important observation or fact, characteristic equation. So if we take chi x as a characteristic polynomial, then pt will divide chi t, or px will divide chi x. This is what I want to say. Because characteristic polynomial satisfies if pt equal to 0, then eigenvalues also satisfies. That will imply p of lambda equal to 0, right? But here chi of lambdas are also 0. From here it is clear that p lambda will divide, or px, the equation will divide chi x. Is it clear that what is happening in this case? Okay, so remember this important fact which we may need for this kind of problems. Minimal polynomial always divide characteristic polynomial. So minimal polynomial is the least degree polynomial for which polynomials, if we apply the polynomials over T, that will give me zero matrix or zero transformation. Okay, so in this case we need to check if characteristic polynomial is same as minimal polynomial. So what are the characteristic values? So eigen values are plus root 5 minus root 5, and if we solve this x square minus x plus 2 equal to 0, then we'll get x equal to minus 1 plus 1 plus minus root over 1 minus 4 into 2, which is 8 by 2, right? So 1 plus minus root 7 by 2. So those are the eigenvalues if we solve this. So those are the eigenvalues, and all those eigenvalues are distinct, right? All the eigenvalues are distinct. Therefore, this will imply this transformation or this matrix is diagonalizable. A is diagonalizable. So, in this case, minimal polynomial becomes the characteristic polynomial. Why this is the case? Something is diagonalizable in that case. Minimal polynomial is same as the characteristic polynomial. Okay, so this is this is the case because those entries are different. Otherwise, we may not conclude. For example, identity is diagonal matrix, but its characteristic polynomial is simply x minus I, x minus 1, right? Identity minus identity is 0. So in this case, for identity metric, characteristic polynomial is for, let me include this example. For A equal to identity matrix, the minimal polynomial mx or px, whatever we denote, px is x minus 1, but characteristic polynomial chi x, this is, suppose it is 3 by 3 identity matrix, then it is x minus 1 whole. So though it is diagonalizable, those can be different, but here the eigenvalues are actually distinct. So we can use this fact in this case. So let px be its minimal polynomial, right? Then it is clear that pt equal to 0. Polynomial of the transformation of the matrix is 0. But we already know if polynomial of some matrix is 0, then polynomial of the eigenvalues are also 0, right? Therefore, all those, if we denote those by lambda 1, lambda 2, and lambda 3, 4 respectively, therefore all those lambda i's are root of p, right? For all I equal to 1, 2, 3, 4. And those are distinct. Therefore, x minus lambda i's, all the product I equal to 1 to 4, since those are distinct, will divide px. But note that characteristic polynomial is also same, right? Characteristic polynomial is also product of this x minus lambda is. So minimal polynomial mx is dividing this polynomial. But in this special case, we are also getting that since the eigenvalues are distinct, therefore we are getting this kind of situation. Since the eigenvalues are distinct. So in particular, what we are getting is, therefore, minimal polynomial is same as product of x minus lambda. We are using those two things. Px equal to chi x, which is, in this case, this is same as product of x minus lambda is. I equal to 1 to 4, and in this case, so using those two equalities, px divides chi x and chi x also divides px, therefore both px and chi x are same. So A is actually true. Now, what is the sum of complex eigenvalues minus sum of real eigenvalues? So let us calculate. Note that okay. Oh, sorry. Those are actually 1 plus minus root 7I. They are complex because we are taking square root of minus 7, which is root 7I. So sum of complex eigenvalues, we need to calculate sum of complex minus sum of real eigenvalues. For B, we are trying to calculate sum of complex eigenvalues minus sum of real eigenvalues. So here the complex eigenvalues are 1 plus minus root 7. So it is actually lambda 3 plus lambda 4 minus lambda 1 plus lambda 2. So if we add those two things, what we get is simply 1 plus 1, that is 2 by 2, right? 2 by 2 is same as 1 minus lambda 1 lambda 2. Sum of those two things will give me 0.
Oh, sum of the roots minus b by a.
Sorry.
Sum of the roots minus coefficient of x by coefficient of x squared.
I don't understand what are you saying.
Without calculating the eigenvalues,
Yes, yes. Without
sum
even
of the
calculating, we can conclude actually. Yes,
yes, sum of the roots
yes. Sum of the roots.
minus b by a.
Yes, that you can do actually. Okay, but here we have already calculated, so it is actually 1 plus 1, which is 2 by 2, which is 1, and plus root 5 minus root 5, that will give me 0 here, right? So 1 minus 0 is 1, therefore it is 1. Now it says that determinant of A is 10. Is it true? Determinant is 10. So we already know that determinant of A is same as product of eigenvalues, right? So what are the eigenvalues? It is plus minus root 5. So root 5 times minus root 5, and then 1 plus minus root 7 by 2. So 1 plus root 7 by 2 times 1 minus root 7 I by 2. So no, this is same as minus 5 times. We also, without calculating, we can also see from here, because just put x equal to 0, that will give me the determinant. 0 and 0. So it is minus 5 times 2, which is 10. It is 4 by 4 matrix, so there will be no sign change. Right? Minus 2. Either you directly calculate the product, or if you do this observation, putting x equal to 0, that will give me the determinant. So just put 0, 0 here. So that is minus 5 into 2, which is minus 2. Ultimately, we are doing the same thing. Okay. Half plus minus root 7 by 2i are eigenvalues. So that is, sorry, we need to find eigenvalues of 2i minus a. So for D, 1 plus minus root 7i by 2 is eigenvalue of a. So eigenvalues of it is 2i minus a. 2i minus a are given by twice 2 times 1 minus lambda, because we know that polynomial of a has the eigenvalues of the form polynomials of lambda. So we are taking polynomials of, so this is the polynomial, so we are replacing a by lambda. So those are the eigenvalues, are 2 times 1 minus lambda, which is 2 minus lambda. So 2 minus 1 plus minus root 7 I by 2, that will give me 3, plus minus is minus plus, so that is same actually, root 7 I by 2. So this option is not, we are getting 3 here instead of 1. Okay. So in this question, B is n by n matrix whose null space NB is defined by this, which is usual null space. And in addition, okay, so instead of B, we are starting with some matrix A. This is only just definition. A is 4 by 4 matrix whose, with some extra information, dimension of some null spaces, and rank is given. So we need to calculate all those things. Okay. So note that dimension of null space A minus 3i, that is same as dimension of the eigenvalue lambda, right? Dimension of eigenspace, dimension of eigenspace corresponding to lambda, which is denoted as E lambda. Okay, so this is in null space of dimension of null space in that is nullity of A minus lambda. So if we use this information 1, from here we get from 1, just a minute. From 1 we are getting that dimension of E lambda, lambda equal to 3, is actually 2. That is the eigenvalue 3 appearing twice. Similarly, dimension of, from this, dimension of E5 is 1. Dimension of, so in this case rank is 3, therefore nullity, it is 4 by 4 matrix. So sum of rank and nullity will be the dimension of the vector space, which is 4. Means in this case it is just n, for n by n matrix, rank plus nullity is n, right? So it is, nullity is 4 minus 3, which is 1. So nullity of A, that is same as dimension of the eigenspace corresponding to 0. You can write A as A minus 0i. So this is 1. We have found this nullity is same as 1. So therefore eigenvalues of the 4 by 4 matrix A are given by this set. 3 appears twice, so 3, 3, 5 appears once, 0, right? So 0, 3, 5s are eigenvalues. So this is Oh, not true. I need to find which are not true. So A is true actually. So this is, we don't need A. Now determinant of A is product of the eigenvalues, but 0 is already there, so determinant will be 0, right? We are doing this multiplication of eigenvalues, so that is 0. So determinant 0, this is also correct, so we need to delete. Now A is not diagonalizable and trace is 11, so let us find the trace. Trace of A is sum of eigenvalues, so 3 appears twice, 2 times 3 plus 5 plus 0, which is 11. So this is also true, so we'll discard it. We are finding which are not true. Now A is not diagonalizable. Is it clear why A is not diagonalizable? So you can see that 3 appears twice. So from here it is clear that geometric multiplicity of 3 is 2. But algebraic multiplicity of 3 is also 2. Right? So what we are getting actually, we know the eigenvalues will look like this because there are no other options. It is 4 by 4 matrix, so 3 cannot appear, 3 or any other entry cannot appear more than whatever is written here. So if we again repeat another extra 3, if we try to increase algebraic multiplicity, then it is clear that there are more than 4 eigenvalues, which is not true. N by n matrix has at most n eigenvalues, right? So we are forcefully getting the set of eigenvalues, not the set, but yes, that because repetition is allowed. So the eigenvalues are given by this kind of multi-set or whatever we say. Okay. So in this case, we have already seen that geometric multiplicity of 3 is 2 and algebraic multiplicity of 3 is also 2. And this is also true for any other eigenvalues. Algebraic multiplicity and geometric multiplicity both are 1. For all eigenvalues lambda, therefore A is diagonalized. So clearly A is diagonalizable, so this is actually true. Means this is not true. Okay. Is there any doubt after this? If not, let us solve the next question. Here the linear transformation is defined by this equation, and we need to find this kind of properties. Okay, so t of 1 by definition it is 1, t of x, the coefficient a1 is only 1, which is 0 here on the right hand side. T x square is x square, t x cube is 0, t x to the power 4 is 1. So matrix representation of t with respect to the standard basis 1x, x square, x cube, x4 is actually 1 0 0 0 0 0 0 0 0 0 0 0 1 0 0 0 this. Okay, so can you see that algebraic, what is the algebraic multiplicity of, so there it is clear that the eigenvalues are diagonal entries which are 1 and 0. Eigenvalues eigenvalues are 0 is appearing 2 times, 1 is appearing 3 times. Okay, now from here it is clear that algebraic multiplicity of 1 is 3, it is appearing 3 times. Now what about this option? So this is correct, t is not diagonalizable. Is it true? So let us see. If we subtract, if we subtract t minus this lambda, lambda is 1, lambda minus I identity. So if you subtract this, then this will look like 0 minus 1 0 0, sorry, 0 minus 1, then 0 minus 1 0, this kind of matrix. So rank of this matrix is 2, nullity of t minus I is also, it is actually 3. Therefore geometric multiplicity of 1, this is t minus 1I, so that is same as 3. So algebraic multiplicity and geometric multiplicity for 1 is same. So we don't have any issue here. Okay, now what happens if we check t minus 0I? So in this case it is clear that nullity of t is actually 3. Sorry, nullity rank is 3, so nullity will be 5. Nullity will be 2. 5 minus 3, which is 2. So again nullity is same as, so from here geometric multiplicity of 0, t minus 0I, so you can write t as t minus 0I. So geometric multiplicity of 0 is actually 2, which is same as algebraic multiplicity of 0. So this is geometric multiplicity and algebraic multiplicity are same, therefore t is diagonalizable. So B is false. Given, it is given that minimal polynomial will look like x times x minus 1. So recall that in this case characteristic polynomial it is product of those x minus lambda i's, so it will look like x minus 0 whole square, which is x square, to x minus 1 whole cube. So minimal polynomial will divide those two things, right? So let us try with x. If we start with x, then it is clear that it is non-zero. So x cannot be minimal polynomial, and also x minus 1 is non-zero. X minus 1 also not a minimal polynomial. Both product must appear because those are distinct eigenvalues. So product must divide the minimal polynomial. Okay. By the same kind of reasoning, we have already seen that if two eigenvalues are distinct, then x minus lambda 1 and x minus lambda 2 must divide the minimal polynomial. But let us try to see if so. Guess this as minimal polynomial. We if this is minimal, then p of the transformation should be 0, right? P of t should be 0. We need to check if this is 0, then the x into x minus 1 will be minimal. So okay. So you can easily calculate that this t times t minus I, if you take the matrix multiplication, then those two matrix multiplication will give me the 0 matrix, right? T times, if we multiply those two matrix, that will be 0, because you can see if you multiply my 0 with this, then the first column becomes 0, then minus 1 with this, here the second column is 0, therefore second column of the matrix will be 0. So eventually you will get the 0 matrix. So pt is actually 0 because t times t minus I equal to 0. Therefore p applied on the transformation is 0, this p. So x into x minus 1 is the minimal polynomial. So C is also false. Characteristic polynomial is this. This is clear. We have already seen. No, sorry, x square into x minus 1. So this is also false. Okay. Okay, let us solve this question. Here, the matrix representation of T is given by this matrix. Let me denote it by A. And we need to show which of the following are correct. Okay. So we know the eigenvalues. So let us start with characteristic equation. Characteristic equation. This is same as determinant of a minus xi equal to 0. So it is 1 minus x minus 1 minus x 0 2 1 0 0 2 equal to 0. From here, what will we get is 1 minus x times minus x 1 2 minus 1 minus x equal to 0. So either x equal to 1, or if we calculate this, then this determinant is x squared plus x minus 2 equal to 0. So if we okay, we actually don't need to find eigenvalues. So we only need to solve this. So this is x minus 1 times x squared plus x minus 2 equal to 0. Okay. So this is the characteristic equation. So T must satisfy its characteristic equation. So let us do the whole calculation. It is x cube plus x square minus 2x, and then minus x square. So this will get cancelled. Then minus x, so it becomes 3x plus 2. So this will be the characteristic equation. So T satisfies its characteristic equation. So we will get t cube minus 3t plus 2 equal to 0. 2 means 2i. 2 times identity. 2 does not make any sense. Okay. So this is the correct answer. But what about others? Can others option, is there possibility of any other option? So here we can see that eigenvalues are actually, one is an eigenvalue. So if T satisfies some equation, then the eigenvalue also satisfies that equation. Right? We have already seen if Pt equal to 0 or some function ft equal to 0, then eigenvalues f lambda will also be 0. Eigenvalue will also satisfy the same kind of equation. Okay. So if we put t equal to 1, for example, if we put t equal to 1, means instead of t, if we just replace it by 1, then we'll get 1 plus 2 minus 3 plus 2. So this is non-zero actually. So C cannot satisfy, so T cannot satisfy this kind of equation. Again, if we put T 1 instead of T, the eigenvalue 1 instead of T, then we'll get 1 plus 3 plus 2, which is again non-zero. So this is also false. Here, if we put T, if we replace it by 1, then what we'll get? 1 minus 2 plus 3 minus 2. So in this case, it is 0. But what about other eigenvalues? So there are several other eigenvalues. If we solve this, then we'll get 1 is an eigenvalue and minus 2 is another eigenvalue. Right? Yes. So if we put minus 2, then what will happen in this case? It will become minus 2 cube minus 2 times 4 plus 3 times minus 2 minus 2 times minus 2. But what is this? Minus 8 minus 8 minus 6 plus 4. This is non-zero. So A is also false. We are using this pair. Every if T satisfies the relation ft equal to 0, then eigenvalues of T also satisfies if lambda equal to 0. Okay, we are using this pair to discard all the other options. And this is actually interesting because if eigenvalue satisfies some equation, matrix may not satisfy that equation. At least we need characteristic polynomial. But the converse part is relaxed. That is, if matrix satisfies some equation, then all the eigenvalues will satisfy the same equation. So the reverse direction is more relaxed and more easy to prove actually. Reverse to that Cayley-Hamilton theorem. Okay, you can. There are several other exercises you can prove actually. So, let me solve this question. It is from Hoffman-Kunz. So we need to see here n is 2 by 2 complex matrix and n square is 0, that is n is also nilpotent. Then n is similar to which complex matrix? Okay. So since n is non-zero nilpotent, n is non-zero, there exists some vector v, that is column matrix, such that n times v is non-zero, right? So choose a basis of this form: v b equal to v is non-zero and np is also non-zero. So this is basis. You need to see why this is basis. If you try to, so those will first, if those two are linearly independent, that will be basis because there are two entries, two different vectors. But we need to show that those two are linearly independent. So if we assume the combination C1p plus C2np equal to 0, then apply n will get C1 times np, which is 0, which is non-zero, but C2 times n square v, this is actually 0 because n square equal to 0. But np is non-zero vector, therefore C1 equal to 0. Now C1 is 0, therefore C2 times np equal to 0 by star. Hence C2 equal to 0. Therefore those two are actually linearly independent vector. Hence it forms a basis for R2. Sorry, C2. Now if we apply n on v, that will give me np. And if we apply n on np, this will give me n square v, which is 0. So matrix representation of n with respect to this basis, it will be, so nv means it is 0 times v plus nv. So it is 0 and 1. So you can write np as 0 times v plus 1 times np, and 0 times v plus 0 times np. So we just put those entries in columns. So that will give me the matrix representation. So from here it is clear that 0 1 0 0, this C is similar to n, because similar matrix is just the same matrix, same transformation with respect to different bases. So we have just given the same transformation, we have taken the same transformation, but we just change the basis. Instead of standard basis, we have taken this kind of basis, and we finally get the answer. And since this is non-zero matrix, so this cannot be 0. P inverse np, if we assume P inverse np equal to 0, then apply the inverses, you will get n equal to 0. So A cannot be the option. Again, if we assume P inverse np is identity, then we'll get just multiply P in the left and P inverse in the right, we'll get n equal to I. So P is also false. Now what about D? So note that rank of P inverse np is same as rank of n, because P is actually invertible matrix. So rank does not change by multiplying with some non-singular matrix. So rank, we have already seen that rank of n must be 1, because with respect to this basis, it is clear that rank must be 1. So, but here the rank is 2. So this is also false. Even you can use same observation to discard those two options. But here it is more clear that this is not possible. 0 cannot be similar to any non-zero matrix. Identity matrix cannot be similar to any non-identity matrix. This is also you can use. So okay, I will stop here. If you have any questions or any doubt, you can ask. Since you don't have any issue, any doubt, let me stop. Thank you for your attention.
Thank you.
Thank you, sir. Thank you very much.